To start. First of all, good afternoon, everybody. Welcome to another exciting afternoon of chemistry with your host, Organic Chemistry, Dr. White. A couple things. First of all, I found out I got a problem with my USB port. I have a spare one, but I got to get a better one. If anybody knows a good USB 4 connector port, besides the Sabrent, which are inexpensive, but they have a problem where the wires break. Uh, Let me know by email. But in case you know, I'll be searching. I'll call my computer guy too. All right. Another thing I would like to ask who's ever dreaming of a white Christmas, stop. Wait until November. Yesterday, Dr. White spent some quality time with my driveway snow blower and a shovel, especially because I'm in a part of the block where it occurs. And that means the first 3 feet of my driveway, when the snow plows come by, get wiped out bad. So I had some fun there, but I can use the exercise. All right, I do have a question for you. Did any of you happen to think about organic chemistry and alkanes when you drove by a gas station? My camera's over here if I look like I'm over here. But did you? Did you think about if you looked at a candle, half of that is alkanes? That's organic chemistry. Did you happen to think about if you use methane, natural gas to cook with, or wherever you live, it's nice and toasty warm because the furnace uses methane, natural gas? That's an alkane. Don't be afraid to think about organic chemistry outside of my class because it's everywhere. I stole that from SpongeBob. And, anyways, that's that. All right. Last week we were talking about nomenclature of double bonds, alkenes. And I'll ask my thumbs up people. Everybody see the whiteboard there? Thank you. Let's see if it works. It wasn't, good, it's working now. All right. And let me do one thing that's better. And the question is, ooh, that reminds me, I think everybody can see the little picture of me, thumb in the upper right-hand corner, wherever you put it on your screen. Obviously, don't forget there's 4 bonds to carbon. And the question would be, what's the IUPAC name for this? And let's just go through it quickly. Ah, double bond. And how many carbons in the longest chain? 1, 2, 3. Remember, even though I show bond angles here, this carbon is connected to this, to this, to this, they're part of the same chain. 4, 5, 6, and this could be 6 too. Longest chain is 6, hexane. It's a double bond. Drop the ANE, put ENE. What carbon is the lead carbon closest to one end of the chain? And the answer is 2. I went the other way, 1, 2, 3, 4, which is smaller, 2 or 4. Hopefully you all agree 2. So this is 2-hexane. Now notice we have one atom, each of the same type on each carbon of the double bond. And when we have on opposite sides of a plane, we call that trans isomerism. And then when they're on the same side, which is that's not the case, we call that cis. And notice these hydrogens are on opposite side of this plane right here. and therefore this is trans to hexene. And we have left, oh, it's your good buddy, the methyl group. And therefore, this is methyl. And what carbon is it on? It's on carbon 5. So this would be 5-methyl trans 2-hexene. Say that 5 times quickly. And we went through this. And later on, maybe next week, we'll do the problem set where you'll have examples. Speaking about problem set, I can't remember if I said I'd do it today or Wednesday. Well, let's make it Wednesday. This way, in case you haven't done the problem set for the alkanes chapter, I think 2, problem set, you should do it before I do it, and I'll do it on Wednesday. Also, Wednesday, it's our first lab. And sometime today or tomorrow, probably tomorrow, I will post in the assignment area of D2L the first lab, which you can download, or wait until after I talk about it on Wednesday. I'll go through it on Wednesday after we have our 50 minutes of lecture. Then we'll do our lab, or I'll go through the lab, and then you'll do that on your own. And most of the labs we have, or I have, YouTube, so you can see stuff that's actually you would be doing in the lab. You're not in the lab, but I think it's safer for us to be home than in the lab right now, especially for me. Quick question, is the clicking sound back or not? Give me a thumbs up if it's clicking. Switch to the other camera. Now the clicking's gone, right? I've been trying different things and it hasn't worked, but we'll get to it. All right. Now, when it comes to nomenclature, remember nomenclature is a fancy word for a name. There are 2 skills organic chemists should have, meaning there's 2 types of questions I can ask on the, again, I'm sorry for the lighting change, but this is a cheap, older camera, not cheaper, just older. But anyways, 2 types of questions. One is, here's the structure, give the IUPAC name, and the other is, here's the name, draw the structure. And let's practice that for alkenes, double bonds. And let me also remind you something you should know. We'll talk about it more in a little while. Double bond, remember 2 lines. One is a pi bond, and one is a sigma bond. And you should know this. And remember, every line or every covalent bond, like a pi bond, is 2 electrons. But anyways, let's go back to nomenclature. And the question would be, draw the and sometimes I'd write, instead of just draw the structure, draw the condensed structure, which means you don't have to show, for the most part, except for double bonds, carbon, hydrogen, single bonds. And here I'll do this one. How do you determine what to draw by the name? Always start from the right, move left. And ENE ending tells you double bond. And if that were ANE pentane, hopefully you've learned the alkane chart by now, that's 5 carbons. And notice the double bond, which ENE tells us is on carbon 2 and it's cis. So if I have 1, 2, because this is where my double bond, and cis means the hydrogens are on the same side. And I'll do them here. I could have reversed it and put this on the top. That's 1, 2, 3. 4, 5. Put in hydrogens because you know there's 4 bonds to carbon. And you're done. And that's how you do it. Now, if you had alkyl groups, you'd handle them just the same way. And since I want to share the fun, why don't you all try this one? Draw the structure for 6-ethyl trans 3-desene. And when you're done, give me a thumbs up or smile if you got your video turned on. And remember, you're doing organic chemistry. And it's hopefully not too painful. All right, anybody need more time? Going once, twice, let's do it. All right, how do you decode this to know what to draw? You start at the right and move left. Oh, ENE ending, that tells you you have a double bond. And if this were ANE, decane, that's 10 carbons. Now, where's the double bond start? At carbon 3, and it's trans. So most of you are going to start this way. You could start from the other side too, but I'll do 1, 2, and now because I have my double bond at carbon 3, and I know this is trans, trans is opposite. And for this class, it's always going to be hydrogens. It could be other things like chlorine or even methyl groups. But for now, for this class, I'll stick to hydrogens. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And as we go this way, notice we have an ethyl group. Hopefully you learned your alkyl groups on C6. And you can put the first carbon and you can put the second one either right or left. Doesn't matter because there's free rotation around the carbon-carbon single bond. And now I have to put in my hydrogens. Remember, it's now your responsibility as a member of my class, if I make a mistake, putting in hydrogens, because I'm going to go at warp drive. And that's how you do it. And that's 6 going here. You start from this end. ENE tells you it's a double bond. That were ANE, decane, 10 carbons, which I have here. And next, where's my double bond start? Carbon 3, and it's trans, which is what I did here. And then on carbon 6, there's an ethyl group. And that's how you do nomenclature. Oh, let's do one more. And I'm going to be becoming a lazy organic chemist, which we are. Instead of putting tert, I'll just call it T-butyl. And why don't you try this one? Draw the structure for 4-tert-butyl cyclohexene. I spelled it wrong. Wow. Time to go back to spelling. I didn't finish it. And so why don't you draw the structure for 4-tert-butyl or T-butyl cyclohexene? And then I'll do it. For those of you turning on your video camera, thank you. Because this way I can tell when you're done by looking at who's working, who's not. And also thumbs up. In a classroom, I'd be able to see you. And I'd be saying, when you're done, look up and smile. And I have all these smiling faces sometimes in my classroom. You don't have to. All right, I think everybody's just about done. I'll give you another 4.7 seconds. 4.2, 4.8. Oh, I went past it. Time's up. All right, let's take a look at how do you draw this molecule. You start from the right and move left. ENE ending tells you it's a double bond. If this were cyclohexane, we have a ring with 6 carbons. And somewhere there's a double bond. Remember, in a ring, one of the carbons is 1, the other always has to be 2. This is one way of drawing it. Most of you probably did it this way. 1, 2, 3, 4. And on this carbon, there's a T-butyl group or tert-butyl. Now, remember that organic molecules are not glued to a piece of paper or whiteboard. They're free rotating. So I could have also done this, which probably none of you did. Dr. White would have. 1, 2, 3, 4. And these are the same molecules. All I've done is rotate this to get to this molecule. And that's how you do nomenclature of double bonds. Did any of you happen to think about or look at a carrot and tell people you're with, hey, look, it's yellow because of double bonds, beta carotene? Or do you happen to look at a tomato and say, oh, it's red because of something with double bonds in it? Or do you open up something or use cosmetic or hand cream lotion or cleaning product and it has that lemony fresh smell? That's due to double bonds too. By the way, if you go to a Super Bowl party or a Zoom Super Bowl party this Sunday, do not tell someone, you know, the carrot you have is that color orange because of double bonds. People do not like hearing organic chemistry during Super Bowl parties. Trust me, I know. All right. Now, I'm going to zoom back up here. And when we're talking about a triple bond, we use now the ending YNE. Remember, triple bond, I have an S, but Let me check. Thumbs up, people. Do you see the ending YNE on your thank you? And this is used for triple bond. Now I have here diene, dies too. I'm not going to talk about that in this class. And similar to double bonds, you select the longest carbon chain that includes both carbons. Now in this case, a triple bond. And you name it as an alkane, drop the ane ending, put yne. And then like a double bond, the number the carbon chain from the end nearest to the multiple bond. In other words, the carbon of the triple bond nearest to the end gets the number. And that's here where you indicate the position. Now, we're not going to have more than one in this class. Alkyl substituents are named the same. Now, good news. Because of the bond angles of a triple bond, you can't have cis or trans. And also because of the number of bonds to carbon, 4. Remember, there's 4 bonds to carbon. And therefore, no cis or trans. So let's look at some triple bonds. And the question is, sometimes I'll write right instead of give. And remember, IUPAC, I'll never ask you. That means the official name. And sometimes Dr. White likes to say, because it sounds cool, IUPAC stands for International Union of Pure Applied Chemistry, which I'll never ask on the test. And here, let's look at a molecule. And one of the things I started training you last week, and now you should continue doing, whenever you look at a molecule, look for what's different. What's not a carbon-carbon single bond or carbon-hydrogen atoms. And look here, ooh, a triple bond. So how do you name this? Find the longest chain with both carbons of the triple bond. 1, 2, 3, 4, 5. Pentane. Drop the ane ending. Triple bond ending is yne. Pentyne. Now, what carbon of the triple bond is closest to the end of the chain? 1, 2 that way. Here would be 1, 2, 3. Which is smaller? 2 or 3. Time's up. And now we're done. The bond angle here, by the way, is 180 degrees. I'll never ask that on a test, but in case you were wondering, it's straight like a cigar or pen or pencil or other things. Don't ask me why, but most people will say cigar, even though Dr. White never liked smoking cigars. And that's how you do it. And the rest of the alkyl groups are the same. Now, let me do one more. Notice this carbon has no hydrogens. Why? Because here I have 3 bonds. Here I have 1. 1 plus 3 equals 4. There are 4 bonds to carbon. 4 minus 4 equals 0. That's why you don't have any hydrogens there. And similar, this one has 3 bonds from the triple bond. 4 minus 3 equals 1, which is why it has. Let's do the nomenclature. All right. How many carbons is the longest chain? 1, 2, 3, 4, 5, 6, or 1, 2, 3, 4, 5. And what's the longest chain? 6. And that would be hexane. It's a triple bond, which has a yne ending. So I'm going to put down hexyne, yne. And then which carbon is the lead carbon closest to the end of the chain? and that would be this one, because that'd be 1. If you started from this end, it would be 6. And I hope you all agree 1 is less than 6. So it's 1 hexyne. And as soon as I say that, that's spoken for, oh, look, something's left over. It's your old friend, the methyl group. And what carbon is that on? If this is 1, this is 2, 3, 4. So that'd be 4-methyl 1-hexyne. Now, nomenclature is not the most exciting thing in organic chemistry, but it's important to learn it because that's how organic chemists communicate. Now, I'm going to have you try one. And remember, it's your solemn responsibility if I make a mistake putting in a number of hydrogens, correct me. All right, question would be, I don't know, we're on C or whatever, give the IUPAC name for the following molecule. Go. And when you're done, give me a thumbs up if you have your video on, or emoji if you don't have your video on. And for those who are quicker than others, please be patient. I try and give everybody time to finish. And if we were in a class face-to-face, I'd be doing the same thing. All right, everybody done? I think so. Let's go ahead and do this. All right, first of all, when you look at a molecule, look for what's different. What's not a carbon-carbon single bond or carbohydrogen? Oh, double bond. And how many carbons along this chain? 1, 2, 3, then 4, 5, 6, 7, 8, 9, 10. That would be 10. Or we could have gone 3, 4, 5, 6, 7, 8. And which is larger, 10 or 8? 10. That's decane. But triple bond, we have a YNE ending. I dropped the ANE and put in YNE. Next, what's the carbon closest to the triple bond, to the end of the chain in the triple bond? And the answer is 2. So that's 2 decyne. And next, oh, look, an alkyl group. Because as soon as I say 2 decyne, all this is spoken for, and this is left over. And what is that? Well, let's make some room. This is an isopropyl group. 3 carbons, 1, 2, 3, to the center carbon to the chain is isopropyl. And what carbon is it on? 3, 4, 5, 6. This would be 6 isopropyl, 2 decyne. Oh, let's do one more. These are fun. And why don't you try 2,2-dimethyl 3-no-9. Draw the structure for that. Remember, di means 2, tri means 3. And when you're done, give me a thumbs up. I already see one person done, but the others, take your time. Oh, a couple other people are done. And for those who came in late, don't forget Wednesday, I will be going through the alkanes problem set. I highly recommend you do it first and ask any questions. Also, commercial from Dr. White. Tonight is 6 and also Wednesday at 6. I have my office hours on Zoom. There's a link listed in the syllabus and also on the front page of D2L for this class. If you have any questions, always feel free to stop by and say hello. All right, I think everybody's done. Let's do this. How do you know what to draw? When you have I went backwards. I shouldn't. Well, anyways, how do you know what to draw? You start this way, Y and the ending. Dr. White just had a brain freeze. And that's 9 carbons. Let's give myself a little room here. 9 carbons, 1, 2, 3, 4, 5, 6, 7, 8, 9. Where's the double bond? Carbon 3. Most of you are going to start from this side. Triple bond, I mean. YNEND, triple bond. Carbon 3. Oh, look. Methyl, that's CH3. Di is 2. And that's how you would do it. Let me move this down here. So those, and this should be a triple bond. I don't know where. And this happens once in a while. If I draw too close to the top there, no, that won't disappear. And that's that. And Dr. White should have really done this. Give the IUPAC name for the following. And why don't you try this one? Give the IUPAC name for this. I see many of you found my YouTube channel for Chem 170, and this by sometime tomorrow evening, this lecture will be posted in that YouTube channel. Unless somebody gives me $1 billion, don't hold your breath on that. Wouldn't mind it, but it ain't gonna happen. FedEx driver comes up, here's a check for $1 billion, enjoy. Yeah, right. Thank you, Cynthia. At least someone enjoys my bad humor. I see someone else smiling, so aren't you glad I'm just not high? Today I'm going to talk about alkynes. This, I would have been asleep already. All right, I think everybody's done. Let's do it. All right, look at a molecule, look for what's different. What's not a carbon-carbon single bond or carbon or hydrogen should get your attention immediately. Triple bond. How many carbons in the longest chain with the triple bond? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's one chain. The other would be 3, 4, 5, 6, 7, 8. And that's the second chain, which is larger, 10 or 8, times up. So that's decane. But since it's a triple bond, it's a Y in the ending, and therefore decyne. What carbon is the lead carbon? That's the smallest number to the end of the chain. This is 3. The other way would be 1, 2, 3, 4, 5, 6, 7, 8. Which is smaller, 8 or 3? Hopefully I'll pick 3. Therefore, this is 4, 5, 6, 7. On carbon 7 is the ethyl group. Hopefully you, if you haven't, I'd highly recommend you do. And it's on carbon 7. So that's 7 ethyl, 3 decyne. Remember, Y in the ending, triple bond. And just to remind you, Dr. White writes the sevens the European or German way, because I had a German teacher in high school who did that from Germany, Herr Brink, and I thought that was cool, and I've been using it ever since. All right, let's do one more now, and I should be in the right, and that is there's 2 skills when it comes to nomenclature. One is here's the molecule, write the IUPAC name. Other is here's the name, draw the structure. Already gave you one, but let's do another one. And why don't you draw the structure for 4-methyl-1-octyne? Remember, triple bond, you can't have cis or trans like a double bond. And when you're done, give me a thumbs up or smile or do both. If you want to frown, that's allowed too. See how easygoing I am? And don't forget, Wednesday is going to be our first lab. I should mention, anything we do in lab will never be on the test for the lecture. And I don't give lab quizzes or lab final. Some instructors do, I don't. All right, I think everybody's done. Let's take a look at this. How do you proceed? Well, organic chemical name, you start from the right, move left. Y in the ending, triple bond. If this were ANE, octane, 8 carbons. I have my 8 carbons. Where is the lead carbon of the triple bond? At the end carbon. And most of you are going to do it here. You could have started here too. And now this is 1, 2, 3, 4. And as we're moving this way, methyl, oh, it's your old friend, the methyl group, and it's on carbon 4. And now I know there's 4 bonds to carbon. Oops, that's not right. Now, over here, this N carbon on the left, if it's in a triple bond or any, you can have it right justified, the hydrogen, or I could have had the hydrogen on this side, left justified. Either one is correct. My software likes to do this. So if I ever do that with an N carbon like that, you might see the hydrogens on the left, but the others throughout the chain are that, and therefore that's how you do it. Let me just do this. And now that's how you do it. And that's how you do nomenclature. Now, as I mentioned, nomenclature is not the most exciting thing in organic chemistry. It's like going into a 4-star restaurant. If you don't know Michelin stars, 4 or 5-star restaurants are really up there. I've been to a few in my life. And if you go in there and order, what do you want? Oh, give me a piece of plain white toast. Boring. It'll keep you alive, but there's much more better things on the menu. Well, nomenclature is like that. It's an important foundation, but now it's time to get into the exciting part of organic chemistry. And that's chemical reactions. And the first type of reaction will be addition reactions. But before we go into this, quick little review about chemical reactions. Everybody see the whiteboard on there again? Thank you. All right, this won't be on a test, but just to remind you, chemical reaction is shown this way. And what this means is compound A and compound B react. This is A and B. And at the base of the arrow, A and B are called reactants. Now, if you've worked in industry most of your life, like Dr. White, I will call them more likely starting materials. And what you may see for both academic and industrial are called the product, or if there's more than one, products. Say here, E and F are the reactants or starting materials. G and H are the products. Whatever at the head of the arrow is the products. Now, organic chemists are lazy, and sometimes when we're running out of room or for various reasons, we'll curve the arrow like that. Also, sometimes we're real lazy, and I don't know where this comes. We sometimes will do this. Put a reactant above or below the arrow. And if you're not sure something I'm doing on the whiteboard or talking about, ask. Because remember, in my class, there's no such thing as a dumb question, and also anywhere in my life. Now, when we come to double bond alkenes, the pi bond, the double bond is made up of a pi bond and a sigma bond. Pi bonds you can break like that. In case you didn't hear me snap my fingers, sigma bonds are not broken in this class. So the first reaction, and one other thing, ours in organic chemistry, and I think this is because if you look at the periodic table, no element has just the letter R. In organic chemistry, R is like X, Y, and Z in math as variables. And that just tells you it can have a bunch of other carbons and hydrogens and other stuff. But if you see this functional group, this is what's going to happen. And so if I have anything, what this means is anything with a double bond, and I'll usually do shorthand, if I react it with some molecule I'll call AB, I can break the pi bond. Notice here I have two bonds here between these two carbons. Oh, every bend in the line, sometimes my software will do that. We'll break the pi bond, and each one of these carbons will get something. In this case, it was A and B. And this is called an addition reaction because you're adding things to it. Now, in this class, I'll never ask you what's the name of a certain type of reaction. Even though I do know them all, I won't. And remember, this is important. In this class, carbon-carbon single bonds are almost never broken, only in combustion, when you burn something, which we already talked about, and something I no longer teach when you react a double bond with ozone. And other than that, so in this class, carbon-carbon single bonds are never broken. And let's talk about our first reaction of double bonds, and that is hydrogenation. And hydrogenation is the addition of hydrogen gas, and that exists as H2 to a double bond. And for this, we need catalysts like platinum or palladium or nickel. And here I show a general double bond, and I'll write it a lot of times this way. If I react it with H2, and notice I'm putting another reactant there, this is historically how we do it, with a catalyst, where the catalyst can be platinum, palladium, or nickel. Remember, one pi bond, one sigma bond. I'll break the pi bond, and each carbon of the double bond gets a hydrogen. And this is hydrogenation. And if I look at the clock, it's time for our break for me to get up and do some stretching. I'll see you in 5 minutes at 1:55, and Dr. White's going to go do some stretching. All right, let's get back to work, everybody. Ring, 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 ring. Like the school marm, the old movies, ring the bell to get everybody into the one room schoolhouse. If you've ever seen the old Western movies, they always show that. So let's get back to hydrogenation. But before that, I'm going to start using some terms once in a while that I should define. I might have done it already in case I haven't. First of all, if I talk about drums in chemical industry, a drum of something is 55 gallons, approximately 450 pounds. Next is a tank wagon. How many of you have ever seen a vehicle that delivers gasoline to a gas station? You know, the long truck with the gasoline in it. That's called a tank wagon. Tank wagons for whatever, gasoline, milk, or chemicals are standardized. 5,000 gallons, 40,000 pounds. And Dr. White has done hydrogenations where one experiment, not experiment, one reaction used 40,000 pounds. That's a whole tank wagon. That's a lot of chemicals. It's a lot of fun too. Uh, Dr. White likes doing that stuff. I do. So whenever you have a double bond, if you react it with hydrogen and a catalyst, platinum, palladium, or nickel, you break the pi bond and one carbon, both carbons double bond, get hydrogen. This is called hydrogenation. How many of you ever heard of hydrogenated fats and oils? And how many of you heard some of them are pretty bad for your health? But anyways, later in the semester, I'll teach you about hydrogenated fats and oils. I've worked in that industry too. Uh, and more than one industry, I've done hydrogenations. But what you're doing is finding a double bond in the fat or oil, carbon-carbon double bond, and making it a single bond by adding hydrogen and a catalyst. And I'll explain later on why people do that to make money. And that's why. And I'll get into that. All right. Now, here's something important. Let's go through on my test. There's three types of questions I usually ask on a test. One is general knowledge, like how many bonds to carbon, or other things like give the name of a product that uses an alkane, gasoline. And then the other type is nomenclature. And you saw the two different types of nomenclature questions I can ask. And that is, here is a molecule, give the IUPAC name, or here's the name, draw the molecule. And there's the third type. And those are what I call reactions. And most of them are, give the organic product or products for a following reaction. And test one, that'll be 50%, 50 points out of 100. But when we get to test two and three, that's usually historically 60, 65 points out of 100. So how do we do a reaction and the type of reactions? Everybody see the 3 points on there? When I write a test, I try and make all the problems smaller points. So if you miss something, it doesn't ruin your score. Now, let's look at a typical oh, who's got their mic on? Oh, I think I know who does. Gotcha. All right. Uh, And here's the question. Give the organic product or products for the following. And here you have that. And now the question is, what do you do? What should you do? Watch closely and learn, please. Now, the first thing, when you're trying to determine the products of an organic chemical reaction, is you look at the molecule and look for what functional group you're dealing with. Another way of saying that is look for what's different in the molecule, what's not a carbon-carbon single bond or carbon-hydrogen atom. That's where the fun is, the action, double bond. And I have a double bond. What am I reacting it with? You look here. And here I have hydrogen gas, and platinum is a catalyst, which I'll abbreviate by CAT. And catalyst can be platinum, palladium, or nickel. And what happens? You break the pi bond. Remember, this is one pi bond and one sigma bond. Pi bonds you can break real easy. Sigma bonds you don't. And each carbon of the double bond gets a hydrogen. Notice there's only one line here, not two, because you broke the pi bond. Now, here's something I need to teach you now. Do you break carbon-carbon single bonds, sigma bonds? No. I'll say that again in slow motion. Do you break carbon-carbon single bonds? No, don't. Once I started brainwashing students that years ago, scores went up because until I did that, students did the wildest things on this type of question. You don't break carbon-carbon single bonds. So what does that mean? I have right here 3 carbons, and each one has a single bond or sigma bond. But I will break one of the pi bonds because that's what my general reaction tells me. And here are my 2 carbons of the double bond. I've broken the double bond, the pi bond. Each one gets a hydrogen. I can do that. And I know there are 4 bonds to carbon, so I can put in the remaining hydrogens. And this is one way of writing the compound, the product. Now, if you want to bring this hydrogen up here and this one up here, you could have also written it with or without the lines like this. Either way is correct. Now, I'd recommend you do it this way because it's one less step for you to mess up and less for you to do.
I'm lost.
What?
I'm lost.
Glad to meet you. I'm Dr. No, I'm sorry. I shouldn't. Let me go through and I'm going to do this again. You're not the only one. This is new. All right. First of all, what you're trying to do is, and I'm going to mute you, so if there's any background noise, it won't come through. Or like if your phone rings like mine might. All right. The question is, give the organic product or products for the following, and you were given this. So how do you figure out what do you make? Because that's what you have to do. And that's the important part. Now I'm biased because I'm a synthetic organic chemist, and that's what you do in synthetic organic. One thing I should point out, I'm going to be teaching a lot of general reactions and how to predict products. Think of those as the building tools that organic chemists use to make molecules. How? Like for this bottle, use general reactions. For the dye on my shirt, top. For the soap you use. For your cosmetics and personal care. And for a whole lot of things. So knowing how to do that is the same as for a carpenter to know how to use a 2x4, a nail, a screw, a bolt to build things. And that's what we do. So let's go back and let me review what I have here. All right, question is, what's the organic product or product? First thing you have to do is find out what's different And what functional group? Double bond. And what are we reacting? Because nothing else is going to react. That's the beauty of functional group chemistry. Everything else comes along for the ride. So double bond, reacting with hydrogen and a catalyst, because that's what platinum is. But just remember, the catalyst can be platinum, palladium, or nickel. And anytime you see a double bond in a molecule and you're reacting with hydrogen and a catalyst, you'll break the pi bond. Remember, this has one pi bond, one sigma bond, and each carbon will get a hydrogen. Now, this carbon and this carbon are connected by a single bond, sigma, that doesn't get broken. Same thing here, one of those bonds is a sigma bond, so therefore I'll still end up with 3 carbons, but I break the pi bond because that's what gets reacted to get me to there. And what happens when you do that, each carbon of the double bond, these two, get a hydrogen. And then you put in the rest of the hydrogen because you know there's 4 bonds to carbon. Does that help? Let's do another one.
Yeah, thanks. Now that I can see the final product,
All right.
it helps me backtrack to see that it needed the bonds broken.
Well, that's why I went through it again.
Thank you.
Now, a favorite trick on a test for organic chemists is put a big scary molecule and students go, ee, because they got freaked out. You shouldn't. If you know what to look for, and let's look at this example. Here's a big scary molecule. I could have made it bigger. But when you look at a molecule, Dr. White's going to try something different. I was going to draw an eye. Dr. White is not an artist. Mother was, but I am not. But anyways, you look for what's different. What's not a carbon-carbon single bond or a carbon or not a carbon or hydrogen. That's where the action is. The only thing in this molecule is a double bond. Nothing else will react with hydrogen and nickel. I'll bet on that. When you hear Dr. White says he'll bet on something, I've already won because that's the only time I bet. Well, I take that back. I'll tell you later on time I've been in casinos in Reno. But that's when I say bet with another person, I already won. So what's really happening is the double bond. Nothing else will react, so you can ignore it. You're reacting with hydrogen and a catalyst. In this case, the catalyst is nickel. And remember, just catalyst can be platinum, palladium, or nickel. You break the pi bond. Remember, this has one pi bond and one sigma bond. You break the pi bond, and each carbon of the double bond gets a hydrogen. So to predict this reaction, do you break carbon-carbon single bonds? No. So immediately I start with 6 carbons drawn this way. I have 6 carbons. Now notice where the double bond is. I broke the pi bond, so I only have 1 bond. And I know from my general reaction, each carbon gets a hydrogen. And now I can fill in the rest of the hydrogens because I know there's 4 bonds to carbon. And I'm done. And that's how you do it. Now, listen carefully. Let's say here we are, wherever you are. Let's assume we're at ECC. We're in Elgin at ECC campus. And I said, yeah, I'd like you to get in your car and take a drive to Spokane, Washington. I don't know. I just picked that because it's far away. I don't think I've ever been in Spokane. A lot of other cities in the United States I have. But let's assume you don't have a GPS, you don't have a map. What's the odds of you getting to Spokane, Washington? Zero. Now, if you did have a map or a GPS, what's the odds? Well, they're pretty high, hopefully 100% if you know how to use a map or GPS. You'll get there in a reasonable amount of time, assuming the weather's good. By the way, who's ever dreaming of a white Christmas, wait until November, please. But anyways, the general reactions I'm showing you are your map or GPS. If you don't know those, you can't do those problems. And therefore, you're going to have to memorize them. How do you do it? Write it down 5 times and say it. Because my tests are not open note, and I put things in my tests. I know if somebody's cheating. Trust me, I've already taught online a couple semesters already, so I learned how to put in surprises or indicators if people are cheating and looking at their notes. You shouldn't be. All right, it's time for me to let you try one. Even though I could on reactions, I generally don't show cis or trans isomerism. And why don't you try this one? What would be the organic product or products for the following reaction? 3 points each. One thing I like to ask all of you, next time you log on, make sure when you log into Zoom, you have a name on there so I can take attendance. I'd appreciate it. All right. I was just going through and taking attendance now. Anybody need more time? Going once, twice, done. All right, look at a molecule and the rest of the semester, and I do this instinctively. I look at the whole molecule, look for what's different. It's not a carbon-carbon single bond or carbon or hydrogen atom should get my attention immediately. Same for you, double bond. The rest is this carbon and hydrogen single bonds. Nothing's going to happen with this reaction. I'm reacting with hydrogen and a catalyst. Remember, the catalyst can be palladium, which it is, platinum, or nickel. And here you break the pi bond. Remember, 1 pi bond, 1 sigma bond, and a double bond. I broke the pi bond. Each carbon of the double bond gets a hydrogen. Do you break carbon-carbon single bonds? No. So therefore, come on, there we go. I have 1, 2, 3, 4, 5 carbons bond together by single bonds, I have 5 carbons. The 2 carbons with the double bond are now these 2 carbons. Notice I broke the pi bond and each one gets a hydrogen. I know there are 4 bonds to carbon. And this is one way. You could have also done this. And that's how you do. Oh, let me show you something else. Let's look at a ring. A ring can have a double bond. If I add hydrogen and say palladium, what's different? Double bond, reacting with hydrogen and catalyst. And now the catalyst can be palladium, platinum, or nickel. And I'll talk about that in a second later on. You break the pi bond, each carbon gets a double bond. Well, here are my 2 carbons of double bond. I've broken the pi bond and I'm done. Because remember, on a ring, you don't show hydrogens. Let's look at this carbon. It's got 1, 2, 3 bonds, therefore you don't show it, but it has 1 hydrogen. Let's look at that same carbon over here. It's got 1, 2 bonds. Therefore, this has 2 hydrogens. So you did add it. Same thing here, 1, 2. So on a ring, you don't show these, but they're there. You have added. And that's how you do it. And I'm going to let you try one. And why don't you have some fun? What would be the organic product or product for the following reaction? Oh, by the way, if you see a smile on my face, that's because we're doing organic chemistry. And this is the fun part, at least for Dr. White, and hopefully for you too. We're just starting out, but you will be surprised the things I'll show you this semester. And when you're done, give me a thumbs up or smile or some other symbol. Like for those of you who know our gang, give me the high sign. If you don't know about our gang, that used to be in the 30s in the movies, a serial that you'd watch before a main feature. No, I wasn't born then. When I was a kid, it was always on TV when you come home from school, and all my friends and myself, we'd always watch our gang with Spanky, Alfalfa, and their dog Spot. It's on YouTube if you want to see it. The remake movie they did a number of years ago was awful. All right, let's do this. Question is, what's the organic product or product for the following reaction? And if we look at this molecule, we'll say, what's different? What's not a carbon-carbon single bond, carbon hydrogen atom? A double bond. And I have a double bond. The rest of it is going to come along for the ride. And I'm reacting with hydrogen and nickel is a catalyst. Remember, the catalysts are nickel, platinum, or palladium. And you break the pi bond, and each atom of the double bond gets a hydrogen. Do you break carbon-carbon single bonds? No, never, almost never. And therefore, I have my ring and my methyl group. Don't forget that, it's coming along for the ride. And the double bond right here, I broke. And I just don't show it, and I'm done. And that's how you do it. Now, if you notice, under each example, I wrote the general reaction right here. Every time in my class, I will always do that. Now, you have to memorize that. How do you do that? Write it down, say it 5 times. And common question I'm asked at this point, when I do a question like this on a problem, on a test, do I have to write the general reaction underneath? And I will tell you this. Some of my very top students I've ever had in 170, if you look at their test, underneath each general reaction, specific reaction, you'll see the general reaction. I'll also tell you this. Some of my best students I've ever had in Chem 170, if you look at their test, underneath the specific reaction, you'll never see the general reaction, but it's in their mind. I know it because they get the question right. So, do you have to write the general reaction? No, but it helps. Now, when I look at that problem, I think it's stored right around here. It pops up, I see that general reaction, boom, 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 and now I can put in the specifics. Remember, learning the general reaction is like learning the roadmap or having the roadmap or the GPS for you to use to get from here to here. Without that, you're lost. And unfortunately, I've seen students who never learned it, and it's not pleasant. It's pretty brutal. So do that. All right, so you learned your first organic chemical reaction, hydrogenation. Like I said, I'll teach you later on about hydrogenation. In fact, my first research project when I got into industry after getting my PhD and leaving academics, because I had planned all along to always be in industry, except a number of years ago it died in Chicagoland, which is why I'm teaching now, plus it's fun, is hydrogenation, but not of a double bond, of something else, and I'll teach you that later in the semester. Any questions about hydrogenation? All right, let's go on to the next general reaction. Now, the next general reaction is halogenation. And again, I'll never ask you what's halogenation, but I'll use those names in class. And that's the addition of halogen gas to an alkene. Now, organic chemists use the abbreviation X, means chlorine, bromine, iodine, and sometimes, most of the time, but sometimes not, fluorine. Those are the halogens from the periodic table. And this general reaction, what it tells you is whenever you have a double bond and you react halogen gas exists as a diatomic molecule, X2 like Cl2, Br2, I2, or F2. You don't need a catalyst for this. Remember, X is fluorine for this reaction, chlorine, bromine, or iodine. I have a pi bond, which I can break, sigma bond, I don't break, and each carbon of the double bond gets a halogen. And that's how simple it is. And everybody hopefully sees the whiteboard on the screen. If not, yell. And if we take this molecule and react it with, bromine gas. Question B, what's the organic product or products? 3 points each. Remember, these are the building blocks that organic chemists use to make things that we use in our daily life. Now, what's different? Ooh, double bond. Remember, what's not a carbon-carbon single bond or hydrogen or carbon should get your attention immediately, like this. Anyways, double bond. What am I reacting it with? Bromine. That's a halogen, which organic chemist is X. Halogens are diatomic, X subs 2, Br2 fluorine. Remember, X here is fluorine, chlorine, in this case, bromine, or iodine. And you break the pi bond. Remember, double bond, one pi bond, one sigma bond. And now each carbon of the double bond gets a halogen. Now, do you break carbon-carbon single bonds? No. So I have 1, 2, 3, 4, 5 across. Each are connected by a sigma bond. The double bond has one sigma and one pi. You don't break single bonds or sigma bonds. So I have 1, 2, 3, 4, 5. Now, here's where it gets important. Which two carbons are the carbons of the double bond? These two. Which are these two. And those are the only two that will get the halogen. In this case, what's the halogen X? It's bromine. So each one gets one bromine. This counts as should be a lowercase r. A halogen is just like a hydrogen, counts as one bond. And I can put in my hydrogens. And that's how I did it. Now, if you did something like this, and just thrown the bromines anywhere, this would be wrong. And I'll mark it wrong totally. And you say, well, shouldn't I get partial credit? And the answer is no. If you're, and I've never taken it, but I think some of you have, a number of you taken anatomy and physiology. I think some of you have. If you were asked to draw the face and put a finger coming out of the top of the forehead, should you get partial credit? No, I wouldn't if I were the teacher. Same way in organic chemistry. The location of things where you're on a molecule are as important as what you're actually putting on there. It makes a difference. Sometimes it's the difference between life and death. And unfortunately, later in the semester, I'll tell you a very sad story how this one company changed something that they shouldn't have and almost killed a lot of children. Got some very sick, sad, stupid story. Stupid in the sense it shouldn't have never happened. All right. So this is called halogenation. It's time for me to let you have some fun. All right, your turn. Give the organic product or products for the following reaction. 3 points each. And when you're done, give me a thumbs up or a smile or something to let me know you're. They don't have any emojis like this. That'd be fun. Have emoji apps for Zoom. Oh, that could be dangerous. Ooh, That's my idea. I'm going to make the money off it. Don't you? No, I'm just kidding. Somebody probably has already done it, I'll bet. And when you're done, look up or give me a thumbs up. I know a couple people are. All right, anybody need more time? Okay, let's do it. When you look at a molecule, you look for what's different. Oh, I see a question. Hold on. Oh, I see someone gave me a thank you. All right, when you look at a molecule, you look for what's different, what's not a carbon-carbon single bond or carbon or hydrogen, double bond. And immediately in my mind, if I look at the rest of the molecule, nothing else is going to react with this reagent. So all I see in my mind right now is the double bond. Iodine gas is halogen. Remember, X is fluorine, chlorine, bromine, or iodine. And therefore, I break the pi bond because I've learned this general reaction, and each carbon of the double bond gets a halogen. Do you break carbon-carbon single bonds? No. So I have 1, 2, 3, 4, 5. I'll end up with 5 and attached the way I started. Where are my 2 carbons of the double bond? These 2. Which are these 2? No, you don't have to put dots on the test, but I'm showing you the mindset of how to do this. The general reaction tells me each one of those carbons gets a halogen. What's my X in this point? Iodine. Now, for some reason, organic chemists usually draw this below the chain unless there's something already there. If you put it on top, I will smile but not mark it wrong. And I know there's 4 bonds to carbon, and I can put in the rest of the hydrogens. Remember, a halogen counts as 1 bond. So that's why this is CH2. This is only CH. And that's how you do it. Any questions? See, organic chemistry isn't that bad. If I say that enough times, you'll believe me. I will. All right, oh, let's do another one. Let's have fun. These are. And why don't you try this one? What would be the organic product or product for the following? But they didn't warn you in ratemyprofessor.com that Dr. White makes you use your brain in my class. See how mean I am? And when you're done, give me a thumbs up or look up. And for those who are quicker than any of the other people, please be patient. I try and give everybody time to finish. And in a classroom, I do the same thing. All right, I think everybody's done. Going once, twice. I see a question first. Up, a thumbs up. All right, let's do it. All right, look at a molecule. You're going to have nightmares hearing me say this, but it's true. And you look for what's different, what's not a carbon-carbon single bond or a carbon or hydrogen atom. Oh, double bond, nothing else there. I'm reacting with what? Chlorine gas, Cl2. And the general reaction is double bond, halogen, break the pi bond. Each carbon of the double bond gets a halogen. Remember, X equals fluorine, chlorine, bromine, or iodine. In this case, it's chlorine. Did I break carbon-carbon single bonds? By the way, look at this big, scary molecule. No, you just see it's just a double bond, an alkene, then this is the only thing going on. Did I break carbon-carbon single bonds? No. So I have 1, 2, 3, 4, 5 across, plus 2 methyls, and where they are is important. 5 across plus my 2 methyls, which are my 2 carbons that double bond, these 2, which are these 2, and therefore double bond, I broke one of the lines, one of the pi bonds, as you can see. Each carbon gets a halogen. A halogen is chlorine. And I put in my hydrogens, so I know there are 4 bonds to carbon. And that's how you do it. This is an H. And that's how you do it. Oh, let's do one more. These are real fun. And the question is, what's the organic product or products for the following reaction? 3 points each. And for those who don't have your video on, give me a thumbs up when you're done. For those of you who do, I can tell when you're done. I think everybody's just about done. All right, anybody need more time? Let me check. Nobody give me a thumbs. All right. Cynthia, are you doing thumbs up, you're done, or thumbs up, you need more time? If you need more time, give me another thumbs up.
It was a thumbs up. I'm done. Sorry.
Yeah, first of all, I have nothing to be sorry about. That's just one of the things of Zoom. Dr. White hasn't learned how to read minds over the internet or in the classroom yet. All right, let's do it. If we look at the small, ooh, it's a big fancy molecule. What do I do? No, you look for what's different and what's not a carbon-carbon single bond or carbon-hydrogen, a double bond. And immediately, that's the only thing that's going to react. What am I reacting with? Fluorine gas. That's a halogen. Remember, X means fluorine, chlorine, bromine, or iodine. And you break the pi bond, and each carbon gets the halogen of the double bond. Do you break carbon-carbon single bonds? No. So I'm going to end up with my ring. I'm still going to have my ethyl group on there. That's CH3, CH2, and still going to be. Now, here are my 2 carbons of the ring double bond, which are these 2. And what does my general reaction tell me? Each one gets a halogen. Well, in this case, it's fluorine. And I'm done. And that's how you do it. Now, not so much for this reaction. Well, I'll teach you later on But from now on, one of the questions you should be asking is, why am I learning this stuff? Well, the obvious answer is you want to get a good grade because someone told you had to take this course to get into either a school or a program. Well, why are you learning this? Well, in the case of halogenation, if you can have molecules, which you can find with double bonds, you can put halogens into them. And a number of years ago, chemists, organic chemists found that certain molecules with a lot of halogens in them are less flammable, flame retardant chemicals. And that's important. An important place, which is a federal regulation, is for children's sleepwear. Many years ago, a lot of children were getting burned and killed, unfortunately, when they either got too close at night because they were in their PJs, pajamas, to a candle, or more likely a space heater, and they'd catch on fire and be badly burned. And chemists found, organic chemists, if you put certain chemicals with a lot of halogens, they will retard. Yes, you're right, Joshua. It's true. They will retard. Nothing will make anything that can burn flame-proof. Nothing, no chemical additive. You could put it in a nitrogen atmosphere, but then you die, which is not a good thing either. But this will do that. And how do you put halogens into a molecule? Well, you just learned halogenation of double bonds if they're in molecules. Now, offshoot of this is organic chemists do this one report by a Swedish researcher, which was interpreted incorrectly. A number of chemical companies said, well, buy my halogenated product. If it's good for sleepwear, it's good for your couch, it's good for your plastic of your monitor or your mouse. I don't know if you saw my mouse. I got a good one, a Death Eater. They're much better than Microsoft mouses, and also Logitech mouses. They're more expensive, but they're worth it. And it will, in a fire, it won't burn. Well, it turned out those chemical companies lied because the chemical report they based it on did not really say that for things like plastic. For sleepwear, yes. For other things, not really. And who found this? About 5, 6 years ago, these 4 reporters from the Tribune, Chicago Tribune, did a fantastic job of figuring this out and letting people know about this. And unfortunately, to this day, companies still put things into monitors and other things, the plastic, to make it flame retardant, which really don't help that much. And you got to pay more for that. Now, there's good things and bad things happening in chemistry, organic chemistry. Oh my God, I looked at the clock. It's about time for another break. See how fast time flies when you're having fun with hydrogenation and halogenations and breaking pi bonds like that. And with that, I think it's just about 2:45 when it's let's take about a 5-minute break, come back at 2:50, and I'll see you then. I'm going to do some more stretching. Ring, ring. Let's get going. Hope you all enjoyed your little break. I got to do some stretching so I don't cramp up. When you get older, things like that happen. If you notice, I'm no longer a spring chicken. I think I just did a generation gap. All right, we've been learning general reactions, and you've learned two general reactions so far. The first one is hydrogenation. The second one is halogenation. And general reactions are the building blocks that organic chemists use to make the things in your daily life. Next time you wash your hands, who made that soap? Organic chemical reactions. I'll teach you that later in the semester. Not to scare you, but I will. Some of the most sophisticated organic chemistry goes into nail polish and personal care products like makeup, hand lotions, and probably some of the most sophisticated organic chemistry is in perfumes, which I'll teach you later in the semester, certain reactions there. But you never thought organic chemistry was responsible for those things. And one other place, which not now, in your stomach, after you chew your food and swallow it, it goes into your stomach and it undergoes organic chemical reactions. And I'll teach you those general reactions and specific ones. I get into a lot of neat stuff in this class. Oh, let's do one more of these. They're fun. Oh, come on. All right. Why are you being... All right, let's go back. All right. Once in a while, because I've got so many things running on this PC, even though it's a pretty good one, it gets confused, and it just did. All right, let me... And why don't you do the following? Give the organic product or products for the following reaction. And let me just ask my thumbs up, people. Can you see that on your screen? Thank you. Remember, look for what's different. That's where the fun is. And when you're done, give me a thumbs up if your video's off, or just look up into your camera. Thank you. Oh my God, you guys are getting the hang of this. Doesn't that feel good? Yeah, how many of you have heard how difficult organic chemistry is? I think some of you have. Is it that bad today? You can say yes if you want. It's allowed by class. But the way I teach it, It should be fun because for Dr. White, it is. All right, I think everybody's done. Let's take a look at this. What do? You look for what's different because the question is, give the organic product or products that are the following. How do you know what's different? What's not a carbon-carbon single bond, carbon or hydrogen? That should get your attention. That's where the fun is and all the action. Double bond. As soon as I look at the rest of this molecule, carbon, hydrogens, carbon-carbon single bonds, carbon, hydrogen single, nothing's going to happen there. But for a double bond, I'm reacting with chlorine gas, Cl2. That's the halogen. Remember, X in organic chemistry, fluorine, chlorine, bromine, or iodine. And that, you break the pi bond, and each carbon gets a halogen. Well, all this, folks, comes along for the ride. I did a standard trick on you, put a big scary molecule, but if you know where to look, it's not big, it's not scary. It's just a alkene, a double bond. Everything else comes along for the ride. Which two carbons are the carbons of double bond? These two. What is my general reaction? Each one gets a halogen. In this case, it's chlorine. I know there's 4 bonds to carbon, so I can put in my hydrogens, and that's how you do it. And also, like I said, this is the chemical instructor's favorite trick on a test, put a big scary molecule. And if you don't know your general reaction and you don't know to look for what's different, you're lost. If you do, it's not that hard, except you have to learn this. Now, how do you learn these general reactions? Well, when you have time, and do it now because you're not going to learn this the day before a test, double bond, halogen, X equals fluorine, chlorine, bromine, or iodine. Break the pi bond. Each carbon of the double bond gets a halogen. Do it again, double bond, halogen gas, X2. X can be fluorine, chlorine, bromine, or iodine. You break the pi bond, and each carbon gets a halogen. And therefore, you see, organic chemistry isn't that challenging once you know how to do a reaction. And remember, that's the fun part, because that's how you make all the things you use in your daily life. Let's move on. Now, if you look at halogenation or hydrogenation, and let me just check, everybody see my slides on your screen? Thank you. You'll see I'm adding the same thing to both carbons of the double bond. Hydrogenation, hydrogen on each carbon, halogenation, halogen. What happens if they're different? You're adding different. And we call that unsymmetrical addition reactions. That means you're adding different things to each carbon of the double bond. I will never ask you what is an unsymmetrical addition reaction, but I will ask you to know how to predict the product or products for it. Now, it turns out a famous Russian organic chemist, stopped in the last couple of decades, but for many, many decades, to honor people who've done great work, we name them. And I will honor that great chemist, Russian chemist, Markovnikov. And Markovnikov, this is back around the late 1800s, early 1900s. That's a little more than 100 years ago, 120 years ago, not that long in the history of mankind or the planet. came up with a rule. Do not write this rule down. Do not write this because I'm going to teach you a better way. But Markovnikov's rule originally stated was when an unsymmetrical molecule of the form HA or HQ adds to unsymmetrical alkene, double bond, then the hydrogen from HA or HQ becomes bonded to the unsaturated carbon that already has the most hydrogen. What? Well, let's look at example. Now you'll learn Markovnikov's rule. Now here I have any molecule with a double bond, and let me rewrite this because I came up with a better way and I'm too lazy to change. If you have a double bond and you're reacting HX, remember X, now in this gas, you don't use fluorine because hydrofluoric acid is one of the most dangerous things around. In fact, the only time in my career as an industrial chemist I ever said I don't want to work on that project was using HF. I didn't. The person who did it actually had a nervous breakdown from the stress of working with HX. I'm glad I didn't. I'm sorry he did. But anyways, and the project turned out to be a bust anyways. So he had a nervous breakdown for nothing, true story. But X for this reaction is chlorine, bromine, or iodine, the other halogens. And what happens is you break the pi bond. Oh, you learned that already. Sigma bonds you don't. And one carbon gets H, the other gets the X. And how do you know which gets which? It follows Markovnikov's rule. Now, I used to write down his whole name, but that took a long time and I'd spell it wrong. So I just put down M's rule. Well, what does this mean? What is Markovnikov's rule? Well, let's go to the whiteboard and I'll show you what it means. Oh, by the way, now you're going to have to use your high-level math skills and know which numbers are greater than other numbers from 0 to 10 or 1. Yeah, 0 to 10. And on a test, if I were to ask you, give the organic product or products that are following a reaction, and here it is, let's call it E or whatever letter I'm up to. What do you do? Well, you look at the molecule and look for what's different. Ooh, a double bond. Whoop, push a button on my stylus, which I didn't want to push. You have a double bond. And the rest of the molecule is nothing important. I'm reacting it with HCl. Remember, H and halogens are X. For this reaction, X can be chlorine, bromine, or iodine. Again, I don't think I've never seen anybody use HF. By the way, HF is dangerous stuff. If you get it on your skin, it will eat all the way to your bone. That's how dangerous it is. And it does other nasty things. But anyways, you break the pi bond. One carbon gets H of the double bond. You don't break the single bond because you never break carbon-carbon. The other gets X, and it follows Markovnikov's rule. Well, how do you do that? Well, do you break carbon-carbon single bonds? No. So I have 3. And notice I broke the pi bond. Here are my 2 carbons and a double bond. And now we have to apply Markovnikov's rule. First of all, how many hydrogens on each carbon of the double bond? Only on that carbon. This has 1. This has 2. Now, here's where you have to use your high-level math skills. Which one is the larger number? Hopefully I'll pick 2. Markovnikov's rule is the carbon of the double bond with the most hydrogens gets this hydrogen, and the other carbon gets the halogen. So since this has more hydrogens, the hydrogen will go there. The other carbon will get the halogen. In this case, it's chlorine, and the chlorine will go there. And I know there are 4 bonds to carbon, so I can put in the rest of my hydrogens, and I will, and that's the answer. Now, let me go through this again. We found we had a double bond. We're reacting with HCl, halogens are X. Here's my general reaction. I break the pi bond. Each carbon gets something. One gets H from the HX, the other gets the halogen. And how do you know which one gets which? It follows Markovnikov's rule. The carbon with the most hydrogens of the double bond gets the H. The other carbon gets the halogen. Now, when I was an undergrad, and I still remember this, I hate to say this decades later, my instructor, good one, at IIT taught us Markovnikov's rule. He said to remember it, remember, the rich get richer, the poor get poorer. And we're talking about hydrogens, not money. And that meant the carbon with the most hydrogens, the rich, gets the hydrogen coming in, and the other one gets the halogen. And he also told us a second way, which he used some, how should I say this, not good English. And he used the other way, I remember, it must work because decades later, I still remember it. Them that has it gets it. Again, them that has it gets it. And we're talking about hydrogens. This one has the most hydrogen, them that has it gets it, the hydrogen. And that's Markovnikov's rule. Now, there are gray areas, and I don't put gray areas on the test here. So let's do another one. I'll do this one, then I'm going to let you have some fun too. And the question is, give the organic product or products for the following. And you look for what's different. What's not a carbon-carbon single bond or carbon-hydrogen? I look there, oh look, a double bond. What am I reacting with? HBr, but I know organic chemists use the abbreviation for halogens, which bromine is as X. And for this reaction, that could be chlorine, bromine, or iodine. You break the pi bond, and one carbon gets H, the other gets, oops, got ahead of myself here. Gets the halogen, and this follows Markovnikov's rule, which the carbon of the double bond with the most hydrogens gets this hydrogen, the other gets the halogen, or as I like to remember, them, the rich get richer, the poor get poorer. And now we have to do our high level math skills. We look at the 2 carbons of the double bond, count how many hydrogens. This has 2, this has 0. Which is the greater number? Time's up, hopefully you all pick 2. So the hydrogen from HX, HBr, will go this carbon, and the other one will get the halogen, bromine. Do you break carbon-carbon single bonds? No. So I have 4 across. Don't forget, on this carbon, I have that methyl. This carbon will get the hydrogen because it's one of the 2 carbons of double bond. Following Markovnikov's rule, this will get the bromine. And I know there are 4 bonds to carbon, so I can put in, notice this carbon right here already has 4 bonds to it, a bromine and 3 carbons. So that's why there's no hydrogen. And that's how you use Markovnikov's rule, otherwise known as the rich get richer and the poor get poorer, which unfortunately our society is beyond just Markovnikov's rule, but I'm going to stay away from that in this class. Now, I'm going to let you have some fun. Oops. And why don't you give the organic product or products for the following? By the way, organic chemists are very conceited. And when it comes to reactions, unless you're doing it in a plant and have to deal with cleaning up or waste on a piece of paper or theoretical, when it comes to inorganic stuff, I don't want to know. All right. When you're done, look up or give me a thumbs up. That's one nice thing in a classroom. I can just look around and tell when people are done. But if you're done early, please be patient. I like to give everybody time. All right, anybody need more time? Quick, hurry up. No, I'm just... All right, I think everybody's done. Let's do this. We'll look at a molecule, look for what's different. What's not carbon, what's not hydrogen, what's not a carbon-carbon single bond, double bond. Anything else there isn't going to react. What am I reacting it with? HI, hydrogen iodide. Remember, organic chemists, a halogen like iodine is abbreviated by X, where X for this reaction is chlorine, bromine, or iodine. And now you break the pi bond. One carbon gets H, the other gets X, and it follows Markovnikov's rule. And in this case, do you break carbon-carbon single bonds? No. I start with 4, I better end it with 4. Here are my 2 carbons of the double bond. Markovnikov's rule says the carbon of the double bond that has the most hydrogens will get the hydrogen from HX, and the other carbon will get the halogen. This has 2 hydrogens, this has 1. You have to use your high-level math skills, which is a larger number. Hopefully you pick 2. And therefore, the hydrogen will go to this carbon. The halogen, in this case, is iodine, will go to this carbon. And now I put in the hydrogens. Remember, these 2 were the 2 carbons originally my double bond. Remember, there's 4 bonds to carbon, and a halogen counts as 1. And I'm done. And that's how you do it. All right. Now, I think I might have mentioned this once or twice before, but I'll mention it again. So first of all, the greatest of all organic chemists around by leaps and bounds is Mother Nature. What she's done is amazing. But I should tell you, Mother Nature and Dr. White love rings. Students don't. No, they don't. You should, but they don't. And let's find out why. We look at the following reaction. The question would be, and I'll do this one, what's the organic product or products for the following? And being a diligent student like you all are and learning organic chemistry, you say, oh, look, a double bond, because I look for what's different, what's not a carbon-carbon single bond or carbon hydrogen. I have a double bond. I'm going to add HX. Remember, X is chlorine, bromine, or iodine. Break the pi bond. One carbon gets H, the other gets the halogen X. How do we know? because it follows Markovnikov's rule, and I abbreviate it by M because Dr. White always misspelled his name, which I shouldn't because he had a great achievement. And so now I have to look at the double bond carbons and see which one has the most hydrogen. Uh-oh, you don't show hydrogens on a ring. What do I do? Oh, no, no. You know there are 4 bonds to carbon. If we look at this carbon, there's 1, 2, 3 bonds to it. 4 minus 3 means 1 hydrogen would be on there if I showed it. If I look at this carbon, this is why students don't like rings because they got to do this extra work. I see 1, 2, 3, 4 bonds to carbon. 4 minus 4 means there's 0 hydrogens on there. Now you have to do your high level math scale, which is a greater number, 1 or 0. And the answer is 1. So do you break carbon-carbon single bonds? No. So I'm going to draw my ring, have my methyl group here. Notice I broke the pi bond of the double bond. Now, the hydrogen would go to this carbon, which is this carbon, but we don't show that on a ring, so I'm not going to. The halogen will go to this carbon that we do show. In this case, it's Br. Now, if you put the halogen over here in the methyl group here for my class, that's okay. And that's how you do it. Now let's look at this carbon right here. How many hydrogens are on there? I see 1, 2 bonds. 4 minus 2 would be 2. We don't show these, which I'll do. This is, by the way, quick, write down in your diary. Dr. White actually showed rings, hydrogens on a ring. This is probably the last time I'll do this semester, maybe once more, but it's very rare. And they were there, but we draw it this way. Because we don't show, and that's how you do it. And now, since I'm a nice guy, I'm going to share. And it's your turn. Give the organic product or products for the following. One of these days, I should bring a tape of game show music, you know, like The Price is Right or anything while they're waiting for the contestants. Dun, 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 dun. No, I'm not going to ruin your day singing. You don't want to hear Dr. White singing. I don't want to hear. I put on my heavy earphones when I want to sing. So that way, even I don't hear myself. For those who don't know it, Dr. White's an audiophile. I have 1, 2, 3, 4, 5 stereos in my home. For those who know stereo, my main number 1 unit is a Marantz 8B and 7C. And Joshua, if you ever have to leave early, it's fine. The rest of this whole lecture by tomorrow evening will be on YouTube, okay? My YouTube channel. And if anybody ever has to leave early, hey, life happens. And which is why I'm glad I'm able to videotape this or tape it. And all right, I think everybody's done. Let's do this. We look at this molecule and say, what's different? What's not a carbon-carbon single bond or carbon or hydrogen? And I see a double bond. What am I reacting with? Hydrogen chloride and HX. Remember, X in organic chemistry is chlorine for this reaction, bromine or iodine. And you break the pi bond, and one carbon gets H, the other gets halogen X. How do you know which? You follow Markovnikov's rule. That's the carbon of the double bond that has the most hydrogens gets the hydrogen, the other gets the halogen. And as I learned years ago, and maybe it'll stick with you too, it also, you can remember, the rich get richer, the poor get poorer as we deal with hydrogen. I'm gonna go technicolor on you. Now here are my two carbons of the double bond. Which one has more hydrogens? Well, you have to know there's 4 bonds to carbon. And if I count 1, 2, 3, therefore 4 minus 3 equals 1. This has 1 hydrogen. If I look at this carbon right here, it has 1, 2, 3, 4. And 4 minus 4 equals 0. So therefore this one has 0. Which is the larger number? Hopefully you pick 1. See how tough the math is in my class? And now I know I don't break carbon-carbon single bonds, so my ring is not broken. Before I taught brainwash people don't break carbon-carbon single bonds, they'd always break rings and get it wrong. And now the hydrogen will go here, which I don't show on a ring, and the halogen will go this carbon, it's chlorine, and I'll show this. And that's how you do it. Now, if you had drawn this like this, it's acceptable because all you've done is rotate this 180 degrees. And either way is correct. And that's how you, oh, let's do one more halogenation of a ring. Here you go. Have one more. Have fun. What is that? A pretty molecule. Now you know I'm an organic chemist. And when you're done, don't forget to give a thumbs up or look up and smile. Take your time. By the way, if your rings don't look as good as mine, as long as I can figure out what you got, that's good for me. I think I've had a few more weeks practice doing rings than you have. Gosh, that was an understatement of the year. And when you're done, don't forget, as some of you are doing now, give me a thumbs up or look up at your camera All right, looks like everybody's done. Let's take a look at this. And if I look at this molecule, I look for what's different. What's that? A carbon-carbon single bond, carbon or hydrogen atom. I see a double bond. Nothing else in there gets my attention. And I'm reacting with HI, hydrogen iodine. Halogens are X. X can be chlorine for this reaction, bromine or iodine. Break the pi bond. One carbon gets H of the double bond, the other gets the halogen. It follows Markovnikov's rule. The carbon of the double bond with the most hydrogen gets the hydrogen, the other gets the halogen. Them that has it gets it, or rich get richer. Oh no, it's a ring. Students don't like it. I look at my two carbons. I count bonds, 1, 2, 3. Remember, there's 4 bonds to carbon. 4 minus 3 is 1. So this has 1. Over at this one, I have this bond, and these two, 1, 2, 3, 4. 4 minus 4 equals 0. Isn't the math hard in my class? And which is a larger number? Hopefully you pick 1. And therefore, do I break carbon-carbon single bonds? No. So I'm still going to have the ring. I'm still going to have the 3 methyl groups, CH3 on the ring, where they are. Here are my 2 carbons of the double bond. This carbon gets a hydrogen. I don't show it. This carbon gets the halogen, which in this case is the iodine. Now, if you put the methyl group down here and the iodine up there, that's fine. Let me do it. Either one of these is correct. You're just rotating it. And that's how you do it. Now, one of the things you'll learn in my class is some life experiences from Dr. White. I'm sort of going to be your mentor. And one of the things that I learned is this is my personal life, and also when I was a senior manager in the chemical industry, is people who accomplish or master things don't give themselves credit for doing something hard and mastering or learning things or doing things. And I've been guilty of that myself, even though over the years I've learned how not to do it that much. And think about it. I've just taught you some very sophisticated, difficult organic chemistry, and you can do it. Doesn't that feel good? Aren't you proud of yourself? I am. I see some of you smiling, and you should. Organic chemistry, when you learn it from someone who knows how to teach it, when you practice it, that's the important thing, is not impossible. Yes, we'll go through some hard things, and learning Markovnikov's rule was challenging, but by practice, you're getting the hang of it. And you should feel good. All right, let's move on. Now, another example of unsymmetrical addition to a double bond is called hydration of a double bond. Hydration means adding water. Now, I need to teach you a couple things. First of all, if we look at this reaction, what's important? A double bond. What are we reacting to? This H plus. What's that? Water. I know what that is. And I'll teach you in a second. This is the product you get. And guess what? It also follows Markovnikov's rule. Now, things I have to teach you right now. H plus is shorthand for an acid catalyst. Examples here would be sulfuric acid, and another acid that I will not teach in here is toluene sulfonic acid or methane sulfonic acid. But example, H2SO4, sulfuric acid, and really what is an acid? A proton donor. And organic chemists are lazy, so we abbreviate where you could use different acids as H plus. And notice I can put reactants above and below the arrow, and I do. And now let's look at water. Now, if you think about water, H2O, I can rewrite it, H and OH. And this is similar to the HCl, where the H goes somewhere in the OH, which is called hydroxyl group. OH is called it's not a functional group, just like a methyl group is not a functional group, but it's called hydroxyl group, and I'll teach you more about that later on. And so, how does this work? Addition of water to double bond, alkene. You take a double bond, need H plus catalyst, because a catalyst is something that makes a reaction go quicker. It is not consumed in the reaction, but if you didn't have this, you could sit around for a couple of months or more and nothing would happen. Put a catalyst in there, it shortens it from milliseconds up to hours, which is a lot quicker. And here you also have water. And remember, water I can think of as H and OH. And what happens is one carbon gets the H and the other gets the OH, and it follows Markovnikov's rule. The carbon with the most hydrogens of the double bond gets the H, the other carbon in this case gets the OH. And let's do examples. And if I were to ask on a test or in real life, when you need to make something with this reaction, can everybody see my whiteboard? Thumbs up, people. Thank you. If we look at this molecule, the first thing I'm going to say is what's different. What's not a carbon-carbon single bond or carbon-hydrogen atom, and we have a double bond. That's the only thing that will get my attention. Reacting with acid catalyst, that's what this is, H plus water. Now, remember water, you can think of as H and OH. And I'm going to break the pi bond. Remember, there's one pi bond and one sigma bond. And one carbon gets the H. Now, in this case, we're dealing not with H and X, but H and OH, hydroxyl group. And the other carbon gets the OH. And this follows Markovnikov's rule. The carbon with the most hydrogen in a double bond gets the hydrogen. In this case, the other carbon gets the hydroxyl group OH. Do you break carbon-carbon single bonds? No. So this has two hydrogens, this has one. Notice I broke the pi bond, and which carbon gets the hydrogen? Well, the one with the most hydrogens, and hopefully you pick this one. The rich get richer, the poor get poorer. The other carbon gets the OH group. And an OH group, hydroxyl group, counts as one bond. There are 4 bonds to carbon. And that's how you do it. Now, you'll learn later in the semester, when you put a hydroxyl group on a carbon, we call that an alcohol. And there are many alcohols, and we'll be learning about alcohols. You will be, I already know about it, in a while, in a couple of chapters. And that's how you do it. Again, using Markov, you have a double bond, acid and water. Water is HOH. You break the pi bond, one carbon gets H, the other gets the hydroxyl group OH, follows Markovnikov's rule. The carbon with the most hydrogens gets the hydrogen from water, and the other carbon gets the hydroxyl group from water. And now I'm going to share and let you try one. And therefore, hold on, this looks ugly as heck. That looks better. What would be the organic product or products for the following reaction? 3 points each. And when you're done, don't forget to smile, give me a thumbs up or give me the high sign. For those who missed it, the high sign from our gang. Gosh, I have been brainwashed in my life by watching too much TV when I was young. Now I just don't have time for it. Even though I did finally break down the last year or so and got a complete set for myself from Amazon on Babylon 5. If you don't know that, science fiction, that's great. Yes, I do have a Fire Stick. I got that last December. And I also got the complete, the Avatar, The Last Airbender cartoons. Dr. White still likes his cartoons. It was good. Yeah, I like to be an airbender and a water bender and an earth bender and a fire bender. For those who don't know what I'm talking about, you're missing great things in life. All right, anybody need more time? Going once, going twice. I see someone still working, so I'll give you another. Everybody's done. All right, let's take a look at this. We look at a molecule. I see the functional group, a double bond. Look for what's different. What's not a carbon-carbon single bond or carbon-hydrogen atom should get your attention. That got mine. I'm reacting with H+, that's acid catalyst and water. Remember, water is HOH. Break the pi bond, because you can break pi bonds. You don't break sigma bonds, never, almost never in this class, other than combustion, never. One carbon gets H, the other gets OH. It follows Markovnikov's rule. The carbon of the double bond with the most hydrogens gets the hydrogen, the other carbon gets the hydrox group, OH. This has one, this has two hydrogens, which is the greater number, time's up. Two, do you break carbon-carbon single bonds? No. So I have 4 across. I have my methyl group. Here are my 2 carbons of the double bond. This one gets H. This one gets the OH. I'll put in my hydrogens. And that's how you do it. Now, I'm going to do something in red because it's wrong. If you had drawn this molecule, now I got to force myself to do something wrong. See, it even says it on the screen. Wrong. This should have been there. That should have been there. I would have marked it 0 points because you showed me you didn't learn Markovnikov's rule. Turns out this is called the anti-Markovnikov product. And there's a way of doing that that I don't teach in this class because I only have so much time, 1 semester. If I had 2 semesters, I'd teach you that. Oh my goodness, if I look at the clock, we've run out of time. Time flies when you're having fun with Markovnikov's rule. But hopefully it's going quick for you because it just seems to go zoom for me. Remember, Wednesday, I'll be going through the practice problem set for chapter 2, alkanes. Make sure you try it beforehand. We'll also do new stuff, and then we'll do our first lab. Sometime tomorrow in the assignment area, Blackboard, I'll post the actual lab. You can download as a PDF or a Word document. You don't have to, but you'll need it later on to actually do the lab. And I'll show you what you're going to be doing. I'll talk more about it on Wednesday. Remember tonight, commercial from Dr. White, tonight at 6 o'clock, I will have my office hour and 15 minutes, also Wednesday. So if you have any questions, come on by. And with that, I'll see you on Wednesday. Gang Gazoon. Be healthy. Goodbye.